Now that we've learned about the normal distribution, we're ready to learn about the central limit theorem, which is a special application of the normal distribution and the basis for confidence intervals and hypothesis testing that we'll be doing for the remainder of the term. If you want to figure out the distribution of the change people carry in their pockets using the central limit theorem and assuming your sample is large enough, you will find that the distribution is normal and bell-shaped. So what are we talking about here? We're talking about finding averages from your population. So you have a population with original values in it, and then you want to take sample means from that population and all of the same size. And you're going to make a sampling distribution of all the sample means that you get from that population when you keep taking samples of a certain size. And they'll be normally distributed if one of the two following things is true. Either the individual values are normally distributed, or if not, you can get away with a sample size that's greater than 30. So you don't need both of these, you only need one or the other. So the sampling distribution of sample means is the shape made by the sample means of all of the possible samples of size n. If the central limit theorem applies, the sampling distribution will be normally distributed with the same mean as the original distribution and the standard deviation divided by the square root of n. In symbols, it looks like this. Now, you've seen notation similar to this before, but the difference here is we're using x bar, which is the symbol for the sample mean, instead of just a regular x, because our random variable in this case would be the actual sample means. And instead of just having sigma here, we have sigma divided by the square root of n. And so this part right here is the main thing that really changes your answers. If you haven't divided your standard deviation by the square root of n, you're going to get the wrong answer when finding probabilities dealing with sample means. So picture this. You have a pile of x values and they make a bell curve. And then you start taking samples of size 9 from this population. And you keep doing it until you've figured out that you have a sample of size 9 of every possible member of that population. So you just keep taking 9 out, taking the sample mean, putting it back, taking another sample of 9, finding that mean, and so on until you've done every possible combination. Then all those sample means that you calculated will create its own bell shape that'll be more narrow because the standard deviation will be smaller. Here's an example. Adult IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. In the past, we've been asked questions like this. Find the probability of a randomly selected IQ being less than 110 points. In notation, you have the P of x less than 110 with a mean of 100 and a standard deviation of 15. The IQ scores are normally distributed, so we can use the bell curve to answer this question. And furthermore, we can answer the second question using the central limit theorem. Find the probability that 9 randomly selected IQ scores have a mean less than 110 points. So notice the difference in the wording there. In the part A, where we're talking about 1 randomly selected IQ being less than 110 points, and in B, we're asking about 9 randomly selected IQ scores having a mean less than 110 points. So the notation looks almost identical except for the bar over the x here, and being careful to take the standard deviation and divide it by the square root of the sample size. So, although the sample size is less than 30 here, the individual IQ scores are normally distributed. Therefore, the central limit theorem does apply, and the sample means will be also normally distributed. So here's our original pile of x values, our original pile of IQ scores, and here's our pile of all the sample means of 9 IQ scores. Adult IQ score, this is the same example, just continuing on. Side by side, we'll look at them. So you can see the differences in the wording there, the differences in the parameters. The only difference is the standard deviation is smaller, so the shape is different. And also, when you lay out your z-scores and the corresponding x values, you have a different stretch here. 100, 115, 130, 145. But on the central limit theorem side, we have 100, 105, 110, 115. So what this does is it puts 110 at a relatively different position for part A than it is for part B. So notice that the area for part A is much smaller than the area for part part B. So that's why you have to really make sure you're reading the question correctly so that you're using the correct standard deviation to get the correct area. Here's another example. With annual incomes in thousands of dollars of graduates 1 year after earning their MBA, having a mean of 63 and a standard deviation of 21. Now keep in mind this is in thousands of dollars. The distribution is right skewed. Part A, find the probability of a randomly selected salary being less than $67,000. In Part B, find the probability that 49 randomly selected salaries have a mean less than 67. So the answer for Part A is we can't use the normal distribution to answer that because it's not normally distributed. It said it was right skewed. Moving on to Part B though, since we have a sample size greater than 30, we can use the central limit theorem to find the probability that the sample mean will be less than 67. So we adjust the original standard deviation of 21, we divide it by the square root of n, and get a standard error of 3. So although the salaries are not normally distributed, the sample size is greater than 30, so the means of the salaries will be normally distributed. So for part B, we would answer this by finding the probability that the sample mean will be less than 67. 67 calculates to have a z-score of 1.33, so you could look that up in the z-score table to get an area of 0.9082. Or you could use Excel with norm.dist with the value 67, the mean, the standard error, and true for cumulative as always. And we get a similar answer there, and either one of these should be good enough to enter into your electronic homework.